Welcome back to Talk Tensors. Today, we're going to be taking a deep dive into Haptic, predicting 4D hand trajectory from monocular videos. Now, this paper really caught our eye. It's tackling a challenge that's, pretty central to so many areas of AI and robotics, and that is how to accurately capture and understand all the nuances of human hand movement.
Yeah, it's a fundamental problem, isn't it? We take for granted how effortlessly we use our hands, but to actually replicate that dexterity in machines, it's proven to be incredibly complex.
Absolutely. And, Haptic presents a really innovative approach to predicting not just where a hand is in 3D space, but how it moves through that space over time. That's that 4D aspect. So
Right.
let's break down why this is such a big deal.
We'll consider the applications. If we
Yeah.
can accurately predict 4D hand trajectories, it just opens a world of possibilities in robotics. So robots could learn complex manipulation tasks just by observing humans, leading to, advances in manufacturing, surgery, you name it.
Yeah. And let's not forget the potential in AR/VR. Imagine interacting with virtual objects using your bare hands, with a level of precision and naturalness that truly blurs the line between the digital and physical worlds.
Right.
Pretty amazing. But before we get too carried away with all the possibilities, let's rewind a bit and understand the problem Haptic is trying to solve.
Okay. So traditionally, one of the common methods for estimating hand positions in 3D has been this weak to full transformation. So in simple terms, you take a 2D image of a hand and you try to project it into 3D space using information about the camera's focal length. And the scale of the hand in the image
Okay.
sounds straightforward enough, but
There's a catch.
there's always a catch. The issue is that those values, the focal length and the hand scale, can be hard to determine accurately, especially in real-world scenarios where the camera might be moving or at different distances from the hand.
Okay, I'm starting to see the problem. And the paper actually has a really helpful visual in Figure 3 that illustrates this. It shows how even slight variations in perceived scale, which might look almost identical in a 2D image, can lead to huge discrepancies when you try to project those hands into 3D, using this weak two-fold method.
Right, and the errors become even more pronounced when you're dealing with long focal lengths. Like when the camera is zoomed in, those inaccuracies can make it nearly impossible to create reliable 3D hand trajectories.
So that's the hurdle Haptic is trying to overcome. But how does it do it?
Well, Haptic takes a different tack altogether. So instead of relying on this potentially error-prone weak to full transformation, it directly predicts the change in the hand's depth relative to the very first frame of the video.
Okay, so it's more about tracking the hand's movement over time, rather than trying to calculate its absolute position in space from each individual frame.
Exactly. By focusing on those relative changes in depth, Haptic becomes much less sensitive to variations in camera distance or focal length, which, as we saw, can really throw off those traditional calculations.
Yeah, that's pretty clever. And this approach has another benefit, right? It's what they call a feed-forward method.
You're right. That means Haptic can predict these trajectories in real time, without needing any time-consuming post-processing optimization steps. It's fast and efficient, which is crucial for real-world applications, where you need those predictions on the fly.
Now, Haptic doesn't start from scratch. It builds upon the work of a pretty powerful image-based hand pose estimator called Hamer. And they actually adapt Hamer for video analysis in a really ingenious way.
This is where things get even more interesting. They introduced two new types of attention layers into the network. The first one, called cross-view self-attention, analyzes multiple frames simultaneously to understand how the hand is moving over time.
It's like giving the algorithm a sense of the hand's motion history, right? It can see where the hand has been and use that information to predict where it's going.
Precisely. And the second attention layer is called global cross-attention. It incorporates information from the entire frame, not just the cropped region around the hand. This provides context. The algorithm can see what else is in the scene and how the hand might be interacting with those objects or the environment.
So it's not just about looking at the hand in isolation, but understanding how it relates to its surroundings. That makes a lot of sense. And this dual attention approach has another advantage, right?
You're thinking about the training data.
Exactly. Annotated video data for 3D hand movements is still pretty scarce. But by using these attention layers, Haptic can be trained on both image and video datasets.
You've hit the nail on the head. That's a huge advantage. It means Haptic can learn from the vast amount of image data that's out there. Even if those images don't have 3D hand annotations, it makes the model much more robust and gives it a broader understanding of hand poses and movements.
So it's like getting the best of both worlds. The detailed motion information from video data and the vast knowledge base of hand poses from image data.
It is fascinating how Haptic blends these different data sources and this clever architecture to achieve such impressive results. But it's important to remember that this success didn't happen in a vacuum. This work really stands on the shoulders of giants. It builds upon decades of research in computer vision and AI.
Yeah, you're right. There's a rich history here. From, those early attempts at recognizing simple hand gestures to the sophisticated systems we have today. It's been quite a journey.
It really has. Remember those early systems that relied on hand silhouettes or even color markers to track movement? They were incredibly limited, requiring like controlled environments and very specific lighting.
Yeah, and the idea of accurately tracking complex hand movements in the wild, like what Haptic is doing, it would seem like science fiction back then.
Absolutely. So let's trace some of the key milestones that paved the way for Haptic. One of the biggest leaps forward was the development of depth sensing cameras. The Kinect, for example, was a game changer. Suddenly, we had affordable and relatively accurate 3D information about the scene, which made hand tracking much more reliable.
The Kinect was awesome. It really brought 3D sensing into the mainstream. But even with depth information, the problem of hand pose estimation remained quite challenging, and that's where the rise of deep learning had a profound impact.
You're absolutely right. Deep neural networks, with their ability to learn intricate patterns from massive amounts of data, they were a perfect fit for tackling the complexities of hand pose estimation. Data sets with millions of annotated images of hands started to emerge, allowing researchers to train models that could generalize to a far wider range of poses and viewpoints.
And Haptic actually builds on one of those powerful image-based modelers, Hammer, which itself is based on transformer networks, another major breakthrough in AI.
Transformers have been incredibly influential, not just in image recognition, but also in natural language processing. And now they're making their mark in computer vision. Their ability to handle sequential data makes them ideally suited for analyzing video frames and understanding the temporal flow of hand movements.
It's amazing to see how all these different technologies and research trends have converged to lead us to Haptic. Depth sensing cameras gave us access to 3D data. Deep learning provided the tools to analyze that data, and transformers brought in the ability to handle the time dimension, allowing us to predict those 4D trajectories.
It's a beautiful confluence of advancements. But it's not just about the technology. There have also been crucial advancements in 3D hand modeling. Remember those early systems that just focused on basic key points, like
Yeah.
the fingertips? They were okay for simple gestures, but they lacked the nuance to capture the full expressiveness of the human hand.
Right, they were like stick figure representations, compared to the level of detail we have now.
Exactly. Now we have sophisticated parametric hand models like Monano, which Haptic uses. These models can capture the full articulation of the hand, including the subtle movements of each finger joint. They give us realistic virtual hands, which are essential for applications like robotics and VR, where you need those fine-grained movements for convincing interactions with objects and environments.
So it's clear that Haptic isn't just an isolated breakthrough. It represents a culmination of decades of research, building upon these foundational technologies and innovations in hand modeling, computer vision, and AI.
And it's not just an academic exercise. This research is addressing a very real need. Accurately tracking hand movements in 3D has the potential to revolutionize how we interact with machines and how machines can assist us in a vast range of tasks.
From robotic surgery to immersive gaming, the applications are truly vast. And now, having explored all that historical context, let's delve back into some of the specific innovations that Haptic introduces. You mentioned earlier that it predicts the change in depth relative to the first frame, rather than relying on those traditional weak two-fold calculations. That seems like a subtle but really important distinction.
It's a crucial distinction. The authors argue that this approach is far more robust and less susceptible to errors, particularly when dealing with those tricky situations where camera distances and focal lengths are varying.
And they back this up with solid results, showing that Haptic significantly outperforms those weak two-fold-based methods in terms of trajectory accuracy.
Exactly. And it's worth emphasizing that Haptic doesn't just predict the hand's trajectory, it also reconstructs the hand pose in each frame. And it manages to do this with remarkable accuracy, even exceeding the performance of some methods specifically designed for single image hand pose estimation.
Yeah, they show some really impressive visual comparisons in the paper. The reconstructed hand poses are remarkably detailed and perfectly aligned with the input images.
This high level of performance is partly due to those cleverly designed lightweight attention layers we discussed earlier. The cross-view self-attention allows the network to analyze those intricate movement patterns across multiple frames, capturing those subtle shifts in depth and pose over time.
And the global cross-attention brings in that broader context from the entire frame, helping the model understand the relationship between the hand and its surroundings.
Precisely. It's that combination of temporal analysis, looking at the movement over time, and spatial analysis, understanding the hand's position in the scene, that allows Haptic to make such accurate predictions.
And I was particularly struck by their ability to train this model using a combination of video and image data.
That's a real game changer. Given the relative scarcity of annotated video data for 3D hand movements, being able to leverage the huge amount of image data available gives Haptic a massive advantage. In terms of robustness and generalization ability, it's like learning from both the close-up details of hand movements in the video data and the broader context and variety of hand poses provided by the image data.
Now, one thing that caught my eye in the paper was how Haptic can actually improve the performance of existing test time optimization methods. Can you explain what those are and why that improvement is significant?
Sure. Test time optimization methods are essentially techniques used to refine the initial pose estimations produced by a model. They try to minimize errors and smooth out the predicted trajectory. Think of it like polishing a rough diamond to bring out its full brilliance.
Okay, so they're like fine-tuning tools that make the predictions even better.
Exactly. But here's the thing. These optimization methods can be quite sensitive to the starting point. If the initial estimates are way off, the optimization process might struggle to converge to a good solution. It's like trying to navigate to a destination with a faulty compass. You might end up lost.
So Haptic provides a better starting point for these optimization methods.
That's precisely it. Because Haptic's predictions are already quite accurate. Thanks to its unique approach and those powerful attention layers, it provides a much more reliable foundation for the optimization process. The optimization methods have a better starting point and can therefore achieve significantly finer and more accurate results. It's like giving those optimization tools a high-quality map and a precise compass to guide them.
That's really impressive. It sounds like Haptic is pushing the boundaries of what's possible in 4D hand trajectory prediction.
It certainly is. And it's also opening up exciting new avenues for research and applications in various fields.
Speaking of applications, let's shift gears and talk about the broader implications of this research. The authors touch on some potential use cases in robotics, AR/VR, and understanding hand-object interactions. What are some of the most promising areas where Haptic could have a real-world impact?
The possibilities are incredibly exciting. In robotics, imagine robots that can learn intricate manipulation tasks, not through tedious programming, but simply by observing human demonstrations. Think of a robot learning to assemble furniture just by watching a YouTube video, or assisting with delicate tasks in manufacturing or even surgery.
That would be revolutionary. It would democratize access to robotics and open up a whole new world of possibilities for automation.
Precisely. And in AR/VR, Haptic could revolutionize how we interact with virtual environments. Imagine using your bare hands to manipulate virtual objects with incredible precision and naturalness. No more clunky controllers. Playing a virtual piano or sculpting in a 3D modeling program with the intuitive control of your own hands.
The level of immersion and engagement would be unparalleled. It would transform gaming, training simulations, and even remote collaboration.
Absolutely. And beyond those specific applications, Haptic also contributes to our broader understanding of hand-object interactions. This is crucial for developing robots that can grasp and manipulate objects effectively. But it also has implications for fields like human-computer interaction and assistive technology.
It's fascinating to think about all the ways this research could impact our lives.
Mm.
And the authors also hint at some future directions, like jointly tracking and reconstructing hand motion, or inferring trajectories in real-world coordinates.
Those are exciting frontiers. Jointly tracking and reconstructing hand motion would allow us to capture even more detail and nuance, while inferring trajectories in real-world coordinates would make it possible to seamlessly integrate hand tracking into real-world environments. The possibilities for robotics, AR/VR, and other fields would expand even further.
It's clear that Haptic is not just an endpoint, but rather a launch pad for a whole new wave of research and innovation. And that brings us to our favorite part of the deep dive, novel notions. This is where we take the core ideas of Haptic and we kind of stretch our imaginations a little bit, explore some, potentially wild but fascinating extensions of this research.
I always enjoy this segment. It's a chance to step outside the bounds of the paper and just speculate on what the future might hold.
Exactly. So let's talk about avatars. Not just like your typical visually realistic avatars, but avatars that move and interact with their environments with like a level of fidelity and nuance that we've just never seen before.
So we're thinking beyond just simple motion capture, right? We already have systems that can capture human movements and map them onto digital characters, but it often looks a bit robotic and unnatural.
Right. What I'm envisioning is a scenario where we combine haptic's ability to predict those 4D hand trajectories with advanced physics simulations and AI-driven animation systems. Imagine a world where an avatar's hand movements aren't just mimicking a human actor, but they're actually generated by a system that understands the underlying physics and biomechanics of those movements.
So the avatar's hands wouldn't just be moving in a visually realistic way. They'd be interacting with the virtual world in a way that's physically accurate and believable. They could realistically grasp objects, feel the weight and texture of those objects, and even learn new skills through virtual practice.
Exactly. Think about the implications for online gaming. Your avatar could become like a true extension of yourself in that virtual world, capable of performing actions and interacting with objects with a level of dexterity and realism that's simply impossible with current technology.
It would be a paradigm shift in gaming, creating a truly immersive and embodied experience. And applications extend far beyond just entertainment. Imagine virtual training simulations for surgeons, pilots, or even athletes.
Oh yeah. They could practice complex procedures or maneuvers in a safe and controlled virtual environment, building muscle memory and honing their skills without any real-world risks. And because these avatars would be driven by a system that understands the physics of movement, they could provide real-time feedback on technique, highlighting areas for improvement, and helping people learn more effectively.
It would be like having a virtual coach built into the system, constantly analyzing your movements and offering personalized guidance. And this concept could even have implications for fields like physical therapy and rehabilitation.
Absolutely. Imagine a virtual environment where patients could practice movements and exercises, guided by an avatar that can adapt to their individual needs and provide real-time feedback on their form and progress.
The possibilities are truly boundless. But of course, we have to acknowledge that building avatars with this level of realism, it's a monumental challenge. It would require significant advances in AI, physics simulation, and animation technology, not to mention the computational power needed to run these simulations in real time.
Yeah, you're right, there are significant hurdles to overcome. But it's a vision worth striving for. And it's a testament to how research like Haptic can spark our imaginations and push us to think beyond the current limitations of technology. Who knows, maybe someday those virtual worlds we see in science fiction movies will become a reality, thanks in part to the groundbreaking work being done in labs like the ones that produced Haptic.
It's a reminder that even the most cutting-edge research is often just a stepping stone to something even more extraordinary. And that's what makes this field so exciting. We're constantly pushing the boundaries of what's possible. And who knows what incredible breakthroughs lie just around the corner.
Well said. And that wraps up our deep dive into Haptic. As always, we'll have a link to the full paper in the episode description for those who want to delve deeper into the technical details.
Until next time, keep exploring, keep questioning, and keep pushing the boundaries of knowledge.